Here's a sci-fi question for you. What would you do if an asteroid was about to hit the Earth? On February 15, 2013, the residents of Chelyabinsk, Russia, looked up to see a small asteroid headed straight towards them. In space terms, small means it was the size of a 6-story building. This was a 10,000 metric ton object, travelling at around 64,370 kilometers per hour through the Earth's atmosphere. Just 19 to 24 kilometers above the city, the asteroid exploded. The force of the blast was 30 to 40 times stronger than the Hiroshima atomic bomb. Luckily, most of the resulting shockwave was absorbed by the atmosphere. Most. 7,200 buildings across 6 cities were damaged by the blast. People rushed out to see the blazing asteroid, only to get hit by shattered glass raining down on the streets below. Over 1,500 people were injured. The dust from the explosion stayed in the atmosphere for months. By some miracle, nobody died. But what happens when the next asteroid comes? What if it actually hit? And what on earth does Bill Nye the Science Guy have to do with all this? It all comes down to Earth's Planetary Defense System. Sounds like it's straight out of science fiction, but it's real. This is how Earth defends itself from an asteroid impact. City killer asteroids. How does an asteroid get to Earth in the first place? They don't just come out of nowhere. Asteroids are leftover debris from the Big Bang, the creation of the universe. Some of them were born from dust condensing into rock, but never growing big enough to become a planet. Others are massive rocks that crashed into each other, breaking into smaller pieces. All these massive space boulders exist throughout our galaxy, orbiting the Sun. So what happens when an asteroid's orbit intersects with Earth's? There are 3 important factors that affect how an asteroid could hit the Earth. The first is the angle of entry. Chelyabinsk was lucky. Its meteorite entered the atmosphere at a shallow angle. It ended up exploding in the atmosphere itself, long before it would have hit the ground. And yet, the resulting shockwave was still strong enough to damage buildings, while the explosion emitted enough light energy to cause sunburns in a second. The second important factor would be the material the asteroid is made out of. In 1908, 100 years earlier than the Chelyabinsk meteor, an even bigger asteroid exploded over eastern Siberia, near the Tunguska River. It flattened 2,150 square kilometers of Siberian forest. The blast was strong enough to throw people into the air. Once again, through sheer luck, the meteorite blew up over a remote area, killing no one. Both the Chelyabinsk and Tunguska asteroids were made of stone, which broke up under the stress of re-entry exploding in the sky. It would have been a different story if they had been made of denser material, rich in metals. The more durable the asteroid, the higher the possibility of it surviving its entry. If the Tunguska asteroid had been made of iron, it would have punched through the atmosphere and hit the Earth. The final and most significant factor for an asteroid is, of course, size. When it comes to asteroids, size is king. One has to be at least 5 meters wide for even a pebble to reach the ground. That's about the size of a car. For a 100% chance of hitting the ground, the asteroid has to be over 100 meters wide. The force of impact would vaporize it. The extreme heat alone would be enough to melt the ground and ignite the area around its crater. Seismic tremors would trigger from the impact, causing further destruction miles from its immediate location. Like a volcanic eruption, the debris tossed into the air would cover the sky. Anything in the direct impact crater would be obliterated. Not even the sea is safe. If the asteroid landed in the ocean, it could cause tsunamis strong enough to wreck nearby coastal areas. Want a more specific example? This is Dimorphos. It's a distinct asteroid that became the target of one of NASA's most important missions, but more on that later. Dimorphos is over 160 meters wide. What would happen if it hit a major city like London? Windows over the entire southeast of England would shatter from the shockwave alone. The damage within Greater London itself would be severe. Buildings would crumble. The heat blast would burn anyone standing in its wake, and the seismic waves would bring down anything and anyone left standing. Central London wouldn't survive at all. The crater would be over 1.6 kilometres wide and over 320 metres deep. Anyone who survived the actual impact would be killed by the powerful air blast that follows after. A terrifying prospect, isn't it? Thankfully, the chances of an asteroid hitting a city are low. The surface of the Earth is 70% water. There are higher chances of an asteroid landing in the ocean than on a populated area. But the chances aren't zero. With the thousands of asteroids that exist in our galaxy, is there anything we can do to protect ourselves that isn't leaving it up to luck? Well, we'd have to find them first. The International Asteroid Tracking Community. In 1998, the US Congress gave NASA a new task: identifying, characterizing, and tracking near-Earth objects, or NEOs, greater than 1 kilometre in diameter whose orbit crosses Earth's. This was further amended in 2005 to become all NEOs greater than 140 metres in diameter. To date, NASA has noted and categorised over 30,000 NEOs. They discover hundreds more every year. So how do they do it? This is the asteroid hunting facility on Mount Lemmon, Arizona. Its camera is capable of scanning the entire sky. A software scans every frame of footage, searching for moving objects. Then, it double-checks against the existing catalogue of celestial bodies. Is this a new asteroid or an old one? If it's a new one, the observer in charge calculates the asteroid's orbit. The data is then sent to the Minor Planet Center in Harvard. The Mount Lemmon facility isn't the only facility searching the skies for asteroids. Astronomers all over the world work together to report their asteroid sightings to the Minor Planet Center. This is where Bill Nye comes in. Welcome to the Planetary Society. It's an international community dedicated to funding space research, not just for organizations, but for individuals as well. Whether it's a professional researcher or a passionate hobbyist, they want to encourage people's love for space. One of their main missions? Decreasing the risk of Earth being hit by an asteroid. By creating an international society of astronomers, they've created an entire community of people who watch the night sky. Night after night, those same eyes keep a lookout for any asteroid they can find. For example, if a new asteroid is spotted, the Minor Planet Center sends a message to the Planetary Society asking if anyone else has spotted it. People from all over the world start sending in their sightings. The Minor Planet Center collates that data and uses it to calculate things like the asteroid's distance from the Earth and the speed that it travels. One example of this system working is through the Kitt Peak National Observatory. It's part of the Spacewatch project, one of the oldest active programs specializing in the study of minor planets, including asteroids. One of their responsibilities is conducting follow-up surveys for new NEO sightings. Their 0.9-meter telescope gives them an impressive sight range for observing the night sky. When a new asteroid gets spotted, they follow its assumed motion for 3 to 4 days. By tracking its movement through the sky, they get more data points on its orbital path. For example, the Kitt Observatory telescope can track an asteroid through 4 data points in just over 20 minutes. Communicating with other astronomers who can also see the asteroid gives them even more data points. The more data points, the better and more accurately the asteroid's orbit can be calculated and predicted. All this data is kept publicly available by the Minor Planet Center. But the Minor Planet Center doesn't just serve as the central database for astronomers across the world. It also serves as the link between the survey aspect of NASA's Planetary Defense System and the active defense aspect. The Center for Near-Earth Object Studies is in charge of putting the Minor Planet Center's data to use. It assesses the hazard potential of all NEOs logged by the Minor Planet Center. How? Through the orbit determination process. They have a custom-built program and algorithm that they feed the data into. The program then propagates that data forwards and backwards, reconstructing the asteroid's orbit. Currently, the centre is processing the data of 1.3 million NEOs. After reconstructing all those orbits, each asteroid then gets sorted into low-risk categories and high-risk categories. High risk means their orbits have a chance of bringing them close to, if not in direct line of collision, with Earth. They can calculate the probability of any object impacting the Earth within the next 100 years. At the same time, the program is capable of spitting out data on whether or not an object will impact Earth within 15 to 30 minutes. This gives us a lot of time to plan and prepare for any possible risks to Earth. Once again, all this data is publicly accessible via the CNEO's website. But the asteroid's orbit isn't the only data we need. Size, composition, surface details, all this information is necessary to understand not just how to defend against them, but to also further determine the secrets of the universe.
We're revolutionizing space. We're doing things differently. Investing in our ideas and innovations to prove and deploy new capabilities faster than ever. Advancing space exploration with new business models and proven technology. Powering a lunar economy and deep space travel. We're shaping the future to make history again.
After all, asteroids are remnants of the Big Bang, over 4 billion years ago. Studying their base material could tell us about what space was like before planets formed. This is where radar comes in. Using radar, NASA can capture not just information, but actual images of asteroids as they pass by Earth. To achieve this, a system of high-power transmitters blast electromagnetic waves at the target asteroid. The asteroid reflects the waves back to Earth. But the waves are distorted according to the different dips and edges of the asteroid's surface. The radar captures these distorted waves and translates them into images for astronomers to study. Even the speed that the asteroid spins can be recorded. The only downside is that radar needs very accurate orbit data and calculations to target an asteroid. Electromagnetic waves have a few seconds to travel 1 million miles to the target. As the waves travel, the antenna also have to be swapped to receiver mode in time to catch them on their return. That's only one image. Still, the data obtained is worth it. Knowing the physical makeup of an object tells us about the potential of its impact. A low-density asteroid means it won't even make it to Earth, while a dense object will punch through the atmosphere and create a crater on impact. In essence, knowing the asteroid means knowing how to mitigate it. Earth's Planetary Defense System. When it comes to monitoring and defending against asteroid impacts, it's an international team effort. But observatories and home telescopes can only go so far. It's actually quite difficult to spot asteroids. They're usually made up of material that's darker than coal, and they don't reflect a lot of light. Telescopes on Earth usually spot celestial bodies by capturing the light of the sun reflecting off of them. So it's difficult for them to spot such dim and non-reflective objects until they get much closer. This lessens the amount of warning time that NASA might have for approaching asteroids. Additionally, the dependence on light means that Earth telescopes aren't strong enough to scan the entire solar system. To properly document and prepare for all the asteroids that might be a threat to Earth, astronomers need that range. Enter the Near-Earth Object Surveyor. It's a space telescope designed specifically to detect, track, and categorize asteroids that come within 30 million miles of Earth's orbit. What makes it different from ground telescopes? Instead of capturing images through sunlight or visible light, it'll capture images of spatial bodies using heat. The NEO Surveyor will be a 50-centimeter diameter telescope operating on 2 heat-sensing wavelengths. This way, the telescope can detect both bright and dark asteroids at distances telescopes on Earth would never be able to achieve. However, the NEO Surveyor isn't ready yet. It's set to launch sometime after 2027. Once it's launched, it will spend the next 5 years surveying the solar system. The goal is to find at least 2/3 of the NEOs in the galaxy larger than 140 meters, aka the City Killers. The telescope's 2 infrared imaging channels will enable it to take accurate measurements of the NEOs. These measurements will include data about their composition, rotation, orbits, and more. The NEO Surveyor will be a huge step towards accomplishing the US Congress's mandate of documenting 90% of all NEOs larger than 140 meters in diameter. Surveying is only the first step, however. What happens when an asteroid is headed to Earth and it's big enough to cause serious damage? In 2021, the world got to see one of NASA's most impactful projects in action, the Double Asteroid Redirection Test, also known as DART. The goal of the DART project was to test the effectivity of NASA's kinetic impact technique in defending against incoming asteroids. Simply put, they wanted to test if crashing a spaceship into an asteroid could change its orbit enough to stop it from crashing into Earth. For an asteroid-smashing spaceship, you'd think the DART would be a massive heavy ship, but the DART itself was actually quite small. Its core was shaped like a box, barely 1 meter wide. It was powered by solar arrays that were capable of expanding, increasing DART's total width to 12 meters. An electric propulsion system would push it through space using a continuous flow of charged ions. But that's the beauty of the kinetic impact technique. A small projectile can go a long way to altering the path of something much bigger. We have the projectile, but what was its target? This is the asteroid Didymos, and its moonlet Dimorphos, otherwise known as a binary asteroid system. This means that Didymos was large enough that it was capable of drawing a smaller asteroid into its orbit. Didymos is about 780 meters, or half a mile in diameter. Meanwhile, Dimorphos has a more humble size, at about 160 meters in diameter, or 525 feet. The binary asteroid system didn't have an orbit that would bring them into direct collision with Earth, but it was going to pass close by. Its orbit's furthest point from Earth takes it only 3 astronomical units, or 3 times the distance between the Earth and the Sun, away. This made it the perfect practice target to test DART. So, NASA prepared the DART for launch. It flew towards its target on a SpaceX Falcon 9 rocket on November 24, 2021. It took almost an entire year to fly towards Dimorphos. The 2 objects' fateful collision finally happened 11 million kilometers from Earth. DART's goal was to measure the kind of effects this impact would have on Dimorphos' orbit around Didymos. NASA decided that the mission would count as a success if DART could change Dimorphos' orbit period by at least 73 seconds. On that day, DART charged for Dimorphos, flying at a high speed of 6.6 kilometers per second. They collided at 7:14 p.m. September 26, 2022. Before DART launched, Dimorphos took 11 hours and 55 minutes to orbit Didymos. After DART's impact, its orbit was reduced to 11 hours and 23 minutes. That's a difference of almost 32 minutes. The mission was a massive success. DART proved that you didn't need a lot of force or material to change the path of an asteroid. The important part was catching the threat early enough so that NASA would have the time to send a spaceship to adjust its course. Other space organizations are quickly following in NASA's footsteps. China is currently building up its own planetary defense system. Their current goal is to follow in DART's footsteps. Plans are in place to build a craft that will impact their chosen NEO, while a separate, second craft will collect data on the asteroid's composition itself. The China National Space Administration, or CNSA, expects their mission to launch before 2030. More recently, they've advanced the timeline up to 2027. Nearby, Russia also has options available. Top missile experts in the country have announced that their most powerful missile could also be repurposed to combat asteroids. Meet the RS-28 Sarmat. It's an intercontinental ballistic missile capable of delivering multiple independent re-entry vehicles weighing up to 10 tons anywhere in the world. It can also carry nuclear warheads. It's easily one of the most terrifying weapons in the world. But that's what makes it capable of combating asteroids. NASA also has other alternative options, though they remain theories for now. A spaceship of significant mass could be used as a gravity tractor for the asteroid. The spaceship would be stationed next to the asteroid. Their mutual gravity attraction will slowly tug the asteroid off its impact trajectory. Of course, building a ship of a significant enough size would cost incredible money and resources. Another option would be the ion beam deflector. A spacecraft could be built with ion engines to propel it towards its destination. Once there, it would blast the asteroid's surface with its engines. This would create pressure and force on the asteroid, changing its trajectory. And finally, there's the classic option, a nuclear bomb. A nuclear bomb would be strong enough to vaporize the asteroid's surface material and jet it into space. This would shove the asteroid off of its flight path. So, why does this matter? In the face of everything happening on Earth right now, the threat of rocks from outer space feels so distant. But just last August, a meteorite made headlines after it exploded over New Jersey, smashing through someone's home. In September, an asteroid the size of a skyscraper passed by Earth at just twice the distance between the Earth and the Moon. Its name is 2025 FA22. It was so close that it actually used to be on NASA's major risk asteroid list. Thankfully, it missed. Finally, just last October 15th, an asteroid flew past Earth at a quarter of the distance between the Earth and the Moon. The worst part of this isn't the distance. It's that NASA only discovered the asteroid 2 days before it passed by. There's a low chance that an asteroid will hit the Earth enough to devastate it, but even if chances are low, it's not zero. Our best weapon against such risks is having the time to prepare for them, which means we need the vigilance that the astronomy community brings. Only by working together across the world can we have the technological power to protect our world. This is how Earth defends itself from an asteroid impact.